We'd like to invite Analytical Space to this stage.
Thank you. Great to be here today. Thank you again for having me. My name is Dan.nevius, and I'm one of the co-founders and the Chief Operating Officer of Analytical Space. And we are building a network of CubeSats that provide a data relay service for remote sensing satellites. But before I start, I want you to imagine. Imagine for a second that you're an inadvertent time traveler, and you wake up one morning in 1960. First thing you do in the morning, you check your phone to see what your emails say or the news, but your app doesn't load. You think that's a little curious. So then you pull up your phone to call your wife to see what's going on, that your app's not working, but the phone call doesn't go through. So then you walk outside, try to order an Uber to get to work, but the car doesn't show up. And then you're starting to panic at this point, so you scream down the street to somebody, "What time is it? I think I've time traveled again." And after looking at you a little funny, they eventually say it's 1960. And then it all makes sense. The infrastructure for your cell phone hasn't been built yet. And so what is an incredibly useful machine has now suddenly become incredibly stupid. And because you become so dependent on it, you by extension also feel incredibly stupid. And so that's kind of what's happening today with remote sensing satellites. Don't get me wrong, these satellites are incredible machines. They do a lot of really useful applications, like disaster response, understanding the conditions after a natural disaster, helping us understand the impact we're having on our planet with climate change monitoring, helping secure the global food supply by understanding crop monitoring and yield forecasting, then also doing things like understanding the weather, or helping us track assets around the globe and make the most efficient utilization of those assets. But they're effectively working with both hands tied behind their back because they don't have the full infrastructure to help them get the most out of what they're capable of. Today, it's mostly a geographical problem. These satellites are in a low orbit because they want to get the best resolution in their imagery. But in that orbit, they're flying around the Earth about once every 90 minutes. And they can only offload data when they have line of sight to a dish on the surface. They're creating incredibly data-intensive and important information, but they only have that line of sight for a couple of hours per day. And because they're not always a ground terminal, there's a significant lag at times between when they collect the data and when they have it on the ground. Can you imagine if your cell phone only worked 2 to 3 hours per day? People would be angry. Why is that okay? Whenever we'd be angry if it's a $1,000 device that's helping us send photos to our family or put on the internet, but whenever it's a sometimes tens, hundreds of millions of dollars device creating data that literally saves lives and helps feed the planet, that we're okay with that low utilization. And the problem is only getting worse. These satellites are innovating on the sensor level to draw out more actionable insights or insights that are more monetizable on the commercial side. And they're increasing in resolution, spatial resolution from meters per pixel down to sub-meter, which can increase it by 100x. They're adding more spectral bands to go from an RGB image where you say that tree looks kind of green to hyperspectral where you can now say, I know that's corn that's nitrogen deficient that needs to be watered. They're increasing the frequency from once a week to now once a day. And some people are looking at video that's 60 frames per second. Or just looking at new instrumentation like synthetic aperture radar or new instruments that aren't optical images that are just inherently data intense. And then on the other side, there's also stringent latency requirements. Some of these applications aren't data intense, but if you don't get the data down within a certain time frame, it's just stale and not useful. So these are things like real-time weather models, real-time tracking of assets, some things for financial intelligence and security. And so if we kind of plot those two metrics on a chart, a lot of satellites start down here in the bottom left corner. The x-axis is the percent of the orbit or day they can be offloading data. The y-axis is the time between when they collect that data and when they have it on the ground. So a lot of groups start with a normal radio, a couple of ground terminals. They quickly realize that's not enough. And so they add ground terminals as much as they can, try to beef up their radio, maybe pump some more power into it. But eventually they just hit a geographical limit where there's just not an extra place where you can put a ground terminal because most of the Earth is covered in water, which sets a cap on how much throughput you can get from your satellite, and also a cap on how fast you can get that data down. And so the whole market is living in this bottom left-hand corner, and there's a lot of applications that we can't unlock. Things like that real-time asset tracking, more accurate weather forecasting, or more data-intensive applications like super high-resolution, multispectral, hyperspectral, and synthetic aperture radar. And so that's what we're working on solving in Analytical Space. So at a high level, we're building a network of small satellites. Our first one's a 6U CubeSat that are backward compatible, that they can receive in RF, so they can help the satellites already in orbit. They're utilizing optical downlink to get a high throughput from the satellite back to the ground to enable high throughput and eventually low latency downlink for remote sensing satellites. And so the ConOps changes a bit. Now the client satellite can have more time to image over the land as they normally would. During times when they usually don't have connectivity, they can now see our satellites and crosslink, for example, over the ocean. And then whenever we fly back over the land, we downlink primarily with optical comm, but with RF as a backup to deal with some cloud coverage issues. And then the client satellite can also offload as normal. And so we position ourselves as an augment to existing ground infrastructure. We say, by all means, dump as much data as you can to the ground whenever you fly over a ground terminal, because you know that works. And you know you can get data down that way. But to get extra data, send it to us during those times when you're idle. And so we help people get extra throughput. So then the question is, how much is that extra throughput worth? If we could get 1 more gigabyte for our customers, how many more square kilometers could they image, and then how much could they sell those square kilometers for? So if you take just one example of a multispectral image, this one's sub-meter resolution, and you do the math on 1 gigabyte of that type of data, it comes out to about 35 square kilometers. And if you look at the market price that's published on the internet, for a freshly tasked image, it's about $50 per square kilometer. If it's freshly tasked over a super high priority location, then it pops up to about 100. So you take the average there. And we find that for every additional gigabyte of downlink that we can create, the client gets an extra 35 square kilometers. And at that price per square kilometer, we create almost $3,000 worth of value for every gigabyte that we help them with. And for us, we're in a strong negotiating position to capture a lot of that value, because at this point, once they've tapped out what they can get going to the ground, their decision for another gigabyte becomes use our data relay service or fly another satellite to get that extra capacity. And flying another satellite often costs them tens of millions of dollars and takes multiple years for them to achieve. And so if you take those numbers of the value created and reasonable assumptions on how much we can capture, and you play that out over today's market of about 600 remote sensing satellites, it's in the single billion dollars per year market size. And then in 5 years, if you look at the growth of the forecast of expected launches, that quickly grows into the tens of billions per year. And so with us, our plan is we can be useful even with a handful of satellites in just incrementally increasing the amount of throughput. We can place them in the customer's orbit so they see us intermittently during those times over the ocean. And that's what we plan on doing over the next year, is launching those first batch of operational satellites. But over time, as we add satellites to the network, our utility increases until we get to the size about 16 data relays in an orbit, where at any time they can see at least one of our satellites. And then if we increase the density, we can then communicate between our own satellites and start routing that data to the ground with low latency. And therefore enabling some of these really useful and cool applications like asset tracking and better weather forecasting, and then just having an incredibly high throughput to enable some of these new data-intensive sensor types. And so our progress to date, so we're not only talking about it, but we're actually building it. Here's our team to date. We have about 10 full-time. Everybody whose name is in black is full-time. Everybody in blue is our great cohort of interns. This team comes a lot of background space engineers who have flown things in space before, worked on national space policy, or worked at commercial space startups before. The interns, we're lucky, we're right in Central Square in Cambridge, right between Harvard, MIT, BU, and HBS. So we got a lot of good talent. And then we also have a great advisory board. The NASA folks here might recognize a couple of faces up there. Pete Warden's the former Senate Director for NASA Ames. Mike French, up until about a year ago, was the Chief of Staff of NASA. Steve Blumenthal was responsible for all of the ground terminal rollout for O3B, so he's advising us on the ground infrastructure piece. Peter Marquez wrote the 2010 National Space Policy. He's also the guy responsible for the laws that were passed for asteroid prospecting and space material property rights. And then Ramana is an HBS professor advising us on fundraising and financing. And then Amanda advises us on IP strategy. And then our investors, we've raised just under $5 million to date from venture capital. Our first round was $500,000 led by Space Angels Network, which is the leading angel group in the space. And then our lead on our seed round was the engine, which started just about a year ago. They're a VC fund started by MIT, where MIT put in money, but it's a separate fund focused on tough technologies that have a longer time horizon and a lot of hardware and tough components. So really great partners for what we're building. And then we've actually flown it in space. So our first satellite launched from the International Space Station over the summer. We got launched as a cargo resupply mission, then deployed off station. This one is a 6U CubeSat, about 10 kilograms, that's demonstrating a couple of new pieces. The first is a deployable antenna that folds up inside the satellite and then pops out to be a half-meter parabolic dish, so we can get high gain link and therefore a high throughput between the customer and us. We have a laser downlink system that we're testing to, once we've stored the data on our satellite, then send it to the ground with super high throughput. And then the third is just the ConOps of coordinating with the client satellite, pointing our satellite at them and tracking to receive their data, storing it on board, and then demonstrating that downlink. So I never pass up the opportunity to show a launch video. So this is the cargo resupply orbital back in May. Which luckily went smoothly because we didn't have insurance, because we're a startup. A couple hours later, the Cygnus capsule docked with the space station. We're in there with the cargo. And then a couple months later, 2 months in mid-July, once the astronauts had time to get to us in their schedule, we were deployed off space station. So that's our little satellite. And we're currently in the commissioning and calibration phase, and we lined up a number of beta test satellites that are going to do technical demonstrations with us. At this point, we have 12 in our official cohort, and we're getting through the FCC kind of licensing and regulation process with those. But then a backlist of around another 30 satellites that have expressed at least verbal interest that we're getting through the process. And on the business development side, we've decided to start with technical demonstrations to show and validate the technology. So as I said, 12 client satellites and a waiting list, a total of over 40. We've also been having great progress on customer interest for the operational satellites. So at this point, we have the majority of the commercial market, or the commercial satellite operators, in our sales pipe, and LOIs and MOUs for pre-booking capacity or using the service that represent over 100 satellites at this point. And we're working with those groups to move towards service level agreements as we start to think about where we deploy our first batch of operational satellites. And so to summarize, we have a team of just under 10 full-time people that in less than 3 years and less than $4 million we've spent has sent a satellite into orbit for a technology demonstration, with actually a second one going up around the beginning of next year. We have a backlist for people wanting to test the capability and significant market traction for the operational service. And so just to loop back to our example of the inadvertent time traveler in the cell phone, who would imagine back before cell phones had this infrastructure, the capability, how much we would use them for? It's become so much more than just calling somebody on the phone, but we can now use them for things like checking our email, reading the news, ordering an Uber, or even things like finding love. A similar thing is playing out with remote sensing satellites in that they're incredibly capable machines, but they lack the basic infrastructure to really unlock the potential of all that they can do. And so today, remote sensing satellites are effectively being designed to the limitations that they have. Imagine if we could remove those limitations and really unlock their full potential. That future is rapidly coming with analytical space. Thank you very much.
I'm curious, what's the lifetime of your satellites?
So this first one off of space station, it's a fairly low altitude. It was around 420 kilometers. So that one will last us, we think, somewhere between 9 months to a year. Our operational ones, we want to put at a higher altitude, probably around 500 to 550 kilometers. And at that altitude, they'll last at least 2 to 3 years, maybe up to 5 years. It's actually kind of a nice feature in that we're using these CubeSats that are fairly affordable and we can have rapid innovation cycles on. And so the plan is, because they're so cheap and because they deorbit naturally, we would just replace them with the freshest version of the technology. So it allows us to be flexible as people decide either to change frequency ranges, or if people decide to adopt optical on their platforms in the future, then we can be flexible and adaptable to those changes with our data relay network.
And the plan is to let them naturally deorbit? Or
Yep.
Dan, over here, what would you say are some of the top 3 points of differentiation between what you're doing and what some of the competitors are doing?
Sure. Yeah, so there's a couple other data relay options. So obviously NASA has Cygnus, which is up in a much higher orbit. But those platforms are much larger satellites, placed in a higher orbit, so they have a really great vantage point. So you need fewer of them to have that coverage. I've never seen an example of a commercial group being able to use Cygnus. I know NASA uses it a lot. But at that distance, you either need a lot of power on your remote sensing satellite to get a high data rate to something so far out. And so we've decided to put our architecture in a lower orbit so that we can be physically closer and enable high intensity payload data transfer. And so that's kind of one piece, the choice between LEO versus higher. There's another group called Odyssey that has kind of that higher out architecture where they're larger satellites, which is better suited for if you want to do TT&C, kind of have a more constant connection into your satellite at low data rates. But not incredibly helpful if you're trying to offload hyperspectral data and really data-intensive stuff. Another key piece and something that we worked a lot on was trying to make our system backward compatible so that we could service satellites that are already in orbit. A lot of the other groups are talking about their own kind of proprietary radio design that you have to then put on your satellite before you can use their network, where we've designed ours to be backward compatible with the frequency ranges that remote sensing satellites have on today. So those are kind of 2 key, one architecture and one just that design to be backward compatible.
I know that this is extremely crowded. I'm over here.
It's hard to find it.
Visible already.
Oh, there you
I
go.
know the lights are bright, aren't they? This is an extremely crowded area right now. I know there's a lot of people working in this. I've been watching it carefully. What problems or issues do you expect, if any, with your optical downlink to the ground? I mean, that's I don't want to say it's cutting edge right now, but it kind of is.
Yeah, definitely, especially on a CubeSat platform, trying to put that all on a 6U. There are a lot of interesting new technical challenges that you have with optical that you don't have with RF. One is that it's such a focused beam, you have to point it very precisely. And so we put a lot of work into the control systems to be able to get that accuracy to actually hit the target. The second is cloud coverage or weather. You can't shoot a laser through clouds like you can with radio. And so you have to either be smart of where you put the ground infrastructure, so statistically you get higher uptime. Our approach is to try to diversify those ground sites so that we can eventually hit something that is cloud-free on a relatively fast time cycle. We also have the ability to go down in RF in case we don't fly over a cloud-free ground site soon enough for the latency requirement. And then as we build out the network, we'll be able to cross-link between our own satellites to route it to where it is cloud-free and really get the most out of using that technology.
Optically between each satellite?
Eventually we want to be optically, but we'll probably do a couple of steps to get there. Yeah, but that's where we hope to build to.
Will you provide backhaul as well on your network?
From the ground and backhaul across?
From your client to you on orbit, are you providing that like a backhaul for them? So you're kind of storing data until you can get it down?
Yeah, we can. We have quite a bit of memory on board, so we can, initially the service is very much a store and forward, where we see them, they offload a bit, and then we have to wait until we physically fly over the ground. But as we build in that density and that crosslink, it can be low latency routing. Yeah.
Can you say what pointing accuracy you require and how much is vibration an issue?
I don't have the pointing accuracy off the top of my head, but I can look it up and tell you at the impact tables. Yeah, but vibration, yeah, does impact our ability to point the laser.
Hey Dan, can you talk about your approach? Can you talk about your approach to cybersecurity and securing the data that you guys are doing? Because obviously that's a huge important part of the trust that you'll be building with your customer set. So can you talk about what you guys are doing on that front?
Yeah, sure. So on this technology demonstration, we haven't done much because we're just trying to validate that we can actually close the link and do that ConOps. But we do have the ability, if the data comes from the client satellite already encrypted, we can just keep it encrypted and kind of pass it forward. And so we're not doing any kind of decryption on the satellite. A lot of these remote sensing satellites have to have a data protection plan under, I think it's NOAA who regulates them. And so we'll obviously comply with all of the parts of that protection plan. One of the interesting things with optical is that it's inherently more secure because you're not broadcasting to a wide area. So when we do go down, it hits a much smaller surface area. And then with the relay, some of our customers have requirements on where the data can come down, especially on the defense side, where they only want it to come down within the continental United States and not any other country, which becomes a huge problem because that further limits the amount of time they have to download to when they're only over that geography. And so we can help them get more throughput to that specific geographical site that they know is secure. So a couple of different ways that we can kind of help at least make sure it's no less secure because we keep the encryption, and in a lot of cases maybe make it a little bit more secure.
I'm curious about who your target customer groups are, and what numbers you're going to need to really be profitable. Because as Richard said, this is a really crowded space.
Yeah.
So when do you expect to achieve that?
Yeah, so our customers so far have been on the commercial side, so commercial satellite operators. The big ones in the US are like Digital Globe, Europe has EGEOS and a lot of new startup players. Quite a few working on synthetic aperture radar, a lot looking at putting hyperspectral on small sat platforms. And so overall, there are probably around 100 or so groups that are operating satellites commercially. And so we've started there because they can move a little faster and we can better understand kind of their economics. But also have applications on the science side with NASA, and then a lot of DoD and defense applications that we're starting to lay the groundwork for. In terms of it being crowded, it's crowded in the sense that a lot of people are using CubeSats, but not really many people are looking at helping remote sensing satellites get data down. There are quite a few that have popped up that are looking at telecom markets that are more focused on Earth connectivity, so remote kind of industrial IoT, where you have a tractor in the field that needs connectivity. So quite a few players have popped up in that area, but that's all designed around that use case of IoT, where we're really focusing on helping remote sensing satellites and designing our network around that application. And then in terms of how much money it costs, so one of the key things we tried to do was try to figure out how can we be useful even with a single satellite, so we didn't have to build 100 of them to turn it on to see if it works. And so we can strategically place the satellite in the customer's orbit. So even with a single satellite, we can help them offload additional capacity, which is valuable to them because any extra picture they get off something they've already spent millions on is additional revenue for them with not that much extra cost. And so the first satellite can be profitable depending on the price that we land on with the customers. And so it's not a hugely capital intensive undertaking as you would think because we use those CubeSats and because we can be useful from a single satellite.
Can you talk a little bit about your timeline and exit strategy?
Yeah, sure. So our timeline, so over the last year, we've done this technology demonstration satellite just to prove the basic concept. We have a second one going up in probably early January. That's another technology demo. It's kind of opportunistic. We plan on launching our first batch of operational satellites that will actually be providing the service and revenue generating, hopefully within the next year. We'll probably do at least one, maybe a couple of those, and then kind of build from there as customers sign up and we know the specific orbits to put them in. And exit strategy, so we have a lot of conversations with partners who may want to try to acquire us. We would ideally, as founders, like to grow it and continue to expand into different applications. So that would be our ideal exit strategy. But there are a number of groups that may want to acquire us in the future, like the ground terminal operators, to extend their capability to in-space connectivity, or even some of the remote sensing operators that would want to have that as a strategic capability for themselves, so that they have that capability when nobody else does.
Dan, how many SAS do you need to have in the air for initial operational capability and therefore revenue generation?
So we've designed it, we only need one. It's a limited capability. It's not 24/7 coverage, but we could provide the basic service where we get extra capacity from that remote sensing satellite, even with a single satellite. Cool. Any other questions?
Thanks very much.
Thank you very much.